Hello everyone. This is the second lecture of week 4. I was mistaken in the previous lecture. There was only one part to the first lecture part of week 4. In this lecture we're going to talk about the main characteristics of random variables. So last lecture we talked about the fact that random variables are unknown, and the most we can say about them, the complete description of them, is their probability distribution. For discrete random variables, that probability distribution was a probability mass function, which consisted of a series of numbers giving us the probability that x takes on each of its possible values. If it's a continuous random variable, we can't do that because each possible value is say, an instant in time. And the probability that something happens at an instant in time is vanishingly small. It disappears to 0. So we have to there talk about a probability density function. And we talked about how to set those up. Normally they're estimated by plotting a histogram and fitting something to them. And we also talked about the cumulative distribution function, or CDF, and that is capital F, and it gives us a way of avoiding integration when we're talking about these continuous random variables and computing probabilities for them. But sometimes we don't know the complete distribution of a random variable, or sometimes we want to know sort of summary information about the random variable. So we're going to talk here about the main characteristics of these random variables, and these are going to be the mean, the degree of variability. We could look at the higher order moments, which are skewness. That's the degree of asymmetry of your random variable, and so on and so forth. Okay, so main characteristics of random variables, these are generally going to be the central tendency, which is a mean or the median, and then measures of variability, which we're going to stick to variance, or standard deviation, which is the square root of variance. So the mean we're going to call mu sub x, so the Greek letter m is mu, and this is the true mean of the entire population. And we saw earlier that this is computed by taking the expected value of x. And the expected value of x is the sum of all possible values weighted by the probability of their taking place. Median, x with a tilde on top of it, is the point dividing f of x in half. So those are two measures of central tendency. Variance, we're going to call sigma x squared, is a measure of variability. And usually we express it as standard deviation by taking the square root, because this has the same units of x. Okay, well, basically if a random variable is more variable, then its probability density function is wider. So it's maybe look like this. The area is still 1, but if it's less variable, then that distribution is narrower. Our random values are concentrated more around the mu of x. And that sigma of x is smaller. F of x that corresponds to these, because this is wider, this f of x is more gradually increasing, whereas because this one's narrower, f of x increases more rapidly near where the action is happening, so near the mean. So the capital F of x is not very informative in terms of the randomness of this random variable. It's hard to see from this where the central tendency is, and also how variable it is, because they always have this sort of S shape. So when I'm plotting random variables, I almost always plot the probability density function, because this gives me an immediate impression about where the central value is and about how random it is. So let's first of all concentrate on the mean. We're going to call the true population mean mu of x, or expected value of x. These two are equivalent, and in fact one is obtained from the other. We haven't talked about expectation yet, but we'll see that shortly. Mu of x is the balance point of the distribution, so this is another way of getting it. Basically, if you take this distribution, cut the shape out, and balance it on your finger, where it balances is the mean. This, you can recall from previous courses in engineering, is also the centroid of that shape, and it can be computed as the first moment of f of x of x. F sub x of x. So if f of x is symmetric, then mu of x is in the middle. That's the balance point. Okay, so here's some examples. This seems to be a symmetric, vaguely symmetric distribution. Mu of x is in the middle. If it's flat like this is a uniform distribution. Mu of x is again in the middle. If f(x) is not symmetric, it may have to be found using the usual principles of finding centroid. For example, here's a distribution that is non-symmetric, and in fact it's triangular in shape. If you recall back to, I don't know, is it statics, where you would compute these moments of areas, the balance point or centroid of a triangle is the 2/3 point. Okay, so 1/3 from the largest end. So we already know where the mean is going to be. We can get this by computing, as we did for a centroid, sum of the xi's times delta ai. So we got a series, we chop it up into a series of little areas, and they're each at a certain distance from the start. Add those weighted distances up and divide by the total area. Well, if this is a probability density function, that total area must be 1. Okay, so the area under f of x must always be equal to 1. So that means that this, and I translate this into a continuous, so the delta ai becomes f of x dx, and then this becomes an integral from 0 to 9, and I multiply by the distance from the start. So x times f of x dx, and add it up from 0 to 9. Underneath here is the area under the PDF, which we know is 1. And so we get 0 to 9 f of x, x times f of x dx, and this must be equal to 6. Okay. In fact, if I plug in the equation for this line here and perform this integration, I will find that this is equal to 6. In general, we can define mu of x is equal to the, oh, I missed something here, is equal to, let's just make this big. Mu of x is equal to the integral, and this should be x fx x dx. Okay, it's the what you see at the top here in our centroid calculation. That's that part divided by 1. Okay, so this is that's the general definition. Basically, it's equal to sum, oops, of all possible values times their probability of occurrence. Okay, and we see that basically it's the sum of all possible values, so that's the x value here. Oops, sorry. That's the x value, that's the all possible occurrences, and this part here is the probability that x takes on that particular value. Okay. So sometimes it's useful to remember this general definition that mu of x is the sum of all possible values times their probability of occurrence. Now I mentioned before the expectation operator. We're going to get mu of x by taking the expected value of x. And in fact we define the expectation operator as so e of x, in words, is the expected value of x, is defined as the integral from minus infinity to infinity of x. So I take this thing here and stick it in here and multiply by the probability of occurrence, which is f of x dx. Okay, I already mentioned this, sum of all possible values times their probability of occurrence. If x is discrete, that sum becomes a discrete sum. So expected value of x is mu of x is the sum of all x times the probability that x equals x. In fact, expectation is more general than what I've shown up above. The expectation of anything, so I put anything in capital letters, so any, in this case, any function of capital X is the anything inside, so the anything comes in here and is made lowercase, multiplied by its probability of occurrence. So, for example, we can look at probably expected value of x squared. So we take the x squared inside, make it lowercase, and then multiply by a probability of its occurrence. So if it's continuous, I get this integral. If it's discrete, I sum up over all x squared times the probability of its occurrence. Similarly, expected value of tan capital X is tan of little x times f of x dx, or the sum over all x of tan x times the probability that x equals x. So let's go back to our usual three-coin toss. What is the mean or expected value of x? And where x is the number of heads appearing in our three-coin toss. So this is a discrete random variable. So expected value of x is the sum from 0 to 3 of x times the probability that x equals x. So the possible values of x are 0, 1, 2, 3, and the probabilities are 1/8, 3/8, 3/8, and 1/8. So I get 0 times 1/8 plus 1 times 3/8 plus 2 times 3/8 plus 3 times 3/8, and that gives me 1.5. And this, although this is not a possible value of x, it makes sense. We know that in general we get half the number of heads showing up. So in any number of coin toss, half the time we get heads showing up. So we have 3 coin tosses, half of them will be heads showing up, so 1.5 on average. Okay, so the next measure of central tendency is the median. I've defined before x with a tilde on top of to be the median of capital X, and it's the point which divides the distribution in half. So it's the point where x less than or equal to x tilde is equal to half, and x being greater than x tilde is equal to half. In general, we can see something like this. If we have an unsymmetric distribution, we sometimes will, this is actually a log normal distribution. The mode is the most likely point. The median is going to be a little bit to the right, and the mean is drawn even farther to the right because this distribution has a long tail that extends off to infinity, so it means the balance point is pulled to the right. If x is a random variable having the following probability density function, so f of x equals lambda e to the minus lambda x, and we'll see in a little while that that is the exponential distribution. It looks something like this, exponentially decaying. And x is greater than or equal to 0, so it's a non-negative random variable. Then what is its mean and its median? So the solution comes as follows. Mean mu of x is equal to the expected value of x, so I take the x and stick it inside here, times f of x, which is this thing here, times dx. Okay, so substitute this thing in here, I get integral from 0 to infinity of x, lambda e to the minus lambda x dx. And then you'll see if you want to solve this, you've got to integrate by parts, but after some manipulation, you'll find out that this is just equal to 1 over lambda. Okay? In other words, this particular exponentially decaying curve has mean equal to 1 over this constant lambda. How about the median? Well, probably the easiest way to find the median is to first of all find capital F of x. Capital F of x is equal to the probability that x is less than or equal to x. So in this picture here, it would be, if this is x here, it would be the area under this curve up to the point x. Okay? So integral from 0 to x of f of x ds, 0, and I've substituted in my little f of x, 0 to x of lambda e to the minus lambda s ds. And this one is easier to integrate. There's no, you don't have to integrate by parts, and you'll find that this is equal to 1 minus e to the minus lambda x. And by the way, this result is shown in the summary pages. Now I mentioned the summary pages. I can't remember if I mentioned it before in one of my lectures, but the summary pages are posted online and include the capital F of x for most of the common distributions. In fact, it includes it for all of the common distributions that we consider, but some of the capital F of x's are in table form rather than an explicit equation, such as the normal distribution. So we know the median is the point x tilde, such that probability that x is less than or equal to 0.5, or probability that x is greater than x tilde is equal to 0.5. We use this because we know capital F of x is the probability that x is less than or equal to x is 1 minus e to the minus lambda x. So the probability that x is bigger than little x is just e to the minus lambda x. And I say that here. So basically, probability that x is greater than x tilde is 1 minus probability that x is less than or equal to x tilde. This is a continuous random variable, so it doesn't matter whether the equality is there or not. We get the same result. But in any case, it's 1 minus this f of x. So 1 minus gives me e to the minus lambda x tilde. And then set that equal to 0.5 and solve it for x tilde. We solve it for the x tilde by taking logarithms of both sides and then dividing through by minus lambda. There's something wrong here as well. Oh no, the 0.693 disappeared. Okay, the minus sign disappeared here. Okay, so basically we get x tilde is 0.693 over lambda is our result. We know one of our lambda is our mean. That's shown here. So that means our median is about 70% of the way to the mean. So it's going to be down about here. So that red line divides this area under the whole curve into half. So 0.5 below it and 0.5 above it. Okay, and I just make a note here. If the distribution is symmetric, then x tilde is equal to mu of x, and usually is then equal also to the mode. Okay, so that covers the characteristic central tendency. The next thing we want to talk about is the degree of variability, and we're going to use variance to measure that. And this is probably the second most important characteristic of a random variable is its degree of scatter. So we can actually look at different measures of variability. For example, we could try the expected value of x minus its mean. So this is the average distance that x is from its mean, and that if x is typically farther away from its mean, it means it's more variable. The big problem with this is, we'll see in a minute, if I take my definition, expected value of anything, and I stick the anything in here and make it lowercase, multiplied by f of x dx, I get the following. Expected value of x minus mean is an integral of x minus its mean, f of x dx. I can break this into two integrals. One of them x times f of x, and the other is mu times f of x. Okay, so that first integral is x times f of x. We've already seen this. This is expected value of x, which is just mu of x. The second part, this mu of x is a constant, so I can bring it outside in front of the integral. And then I'm left with mu of x minus mu of x times integral from minus infinity to infinity of f of x dx. And we know this is just equal to 1. So I end up with this expected value of x minus its mean is just mu of x minus mu of x, which of course is just 0. So this is not a useful measure of variability because it boils down to being 0. And what's the problem? The problem is that the negative values and the positive values, the negative values of x minus mu of x and the positive values of x minus mu of x are canceling each other out. And they will always cancel each other out completely, so that this thing is always going to be equal to 0. Okay, so this is the picture. Basically, we've got a series of observations, for example, in green. Some of them are above the mean, so that this difference is positive, but some of them are below the mean, so that this difference is negative. If I add up all those differences, on average, they will equal the sum of those differences will equal 0. So how do we get rid of this canceling of the sign? Well, we just got to get rid of the sign. And so another possibility is take the absolute value, expected value of the absolute value of x minus mu of x. And this is actually a good measure of variability. It's better actually than the variance. We'll see the variance in a minute where we square that difference, x minus mu of x. The problem with squaring is that if there's any errors in your observations, you are also squaring the errors. So the absolute value is actually better, but the main problem with it is that it's not differentiable at the minimum. And basically, we're often interested in minimizing the variance to achieve quality control. So the higher our quality control is, the less variable our results should be. And if I'm trying to find the minimum variance, I'm looking for the point in this function, which is a minimum, and I do that by differentiating and setting equal to 0. The problem is that the minimum point of this function, although it's easy to see in a picture, is not differentiable, so we can't actually find this mathematically. The slope here goes from -1 and jumps to +1, and is never actually 0. It just jumps from -1 to +1. So at that point, at the minimum point, this thing is undefined, so we can't use our typical math approaches to minimize the variance, find the point of minimum variance of this problem. So the absolute value is not usually used. What we generally use is to get rid of the sign is to square the difference x minus mu of x. So now we're going to define the variance of x, which we'll write as sigma x squared, is the expected value of x minus mu of x quantity squared. So this is now this mean squared deviation from mu of x, and as I mentioned, we square to remove canceling due to the sign. So basically our differences now, we've gone from the absolute, from x minus mu of x, not absolute, but x minus mu of x, and we squared. And that gets rid of the sign. So this would be the same sign as this one here. And in general, if variance of x is large, then x is generally farther away from mu of x and therefore is more variable. In detail, variance of x then is defined as the expected value of x minus its mean quantity squared. I can expand this square, so it's expected value of x squared minus 2x mu of x plus mu x squared. Now, I'm going to introduce a rule here that we're going to see quite a lot of. The expectation of a sum is the sum of expectations. We saw this a little bit up here when we computed this this integral here. This is the expectation of a sum or a difference, but that turned out to be the expectation of x minus the expectation of mu of x. Okay, so we could have immediately have jumped, if we remember that rule, we could have immediately said that thing there is just equal to the expected value of x minus expected value of mu of x, and the second thing is the expected value of constant. Let's just erase this a little bit. The second thing is the expected value of a constant, because mu of x is not random, it's a number. It's like expected value of 2. Well, if that isn't 2, we're in trouble. 2 has to remain to be 2. So that basically this turns out to be expected value of x minus mu of x, and expected value of x is also mu of x, so those things just cancel. Okay, so where are we at? Expectation of a sum. So same thing here. This expectation is an integral. It'll be the integral of little x squared minus 2 times little x times mu of x plus mu of x squared, all times f of x dx. And then I can break it up at each the minus and the plus signs. In other words, variance of x then is the expected value of x squared minus the expected value of 2x mu of x plus the expected value of mu of x squared. I'm going to leave the first one alone. The second one becomes 2x mu of x f of x, and the third one becomes expected value of mu of x f of x dx, mu of x squared f of x dx. Now, the constants can come out front, so the 2 mu of x comes out. I'm left with x times f of x dx inside, and we know already that that's just mu of x. And the last term is the constant mu of x squared can come out front, and then I'm multiplying by this integral of f of x dx over the entire range. We know that the area under f of x has to be 1, so this thing is 1. So this boils down to being expected value of x squared minus 2 mu x squared, so there's mu x times mu x here, plus mu x squared. Okay. Or this is equal to expected value of x squared minus mu x squared. So that basically one of these minuses cancels with the plus, and I'm left with 1 minus mu x squared. And I usually think of it this way: the variance of x is equal to the expected value of x squared minus the expectation squared of x, which is sort of almost like poetry. And I can rearrange this. For example, if I'm looking for expected value of x squared, I can solve it as the variance of x plus the expectation squared of x. Once I have the variance, I can compute the standard deviation as the square root of variance, and the coefficient of variation is sigma x over mu of x. Okay, so let's illustrate this with an example. And this is to find the mean and variance of x, where x is the number of heads showing in a 3-coin toss. We've already done the mean. We saw that the mean was the sum of all possible values times their probability of occurrence, which turned out to be 1.5, which basically was just saying that half of the time we're getting ahead in our coin toss. Variance is a little, we haven't seen this yet. I'm going to use this form. Variance of x is expected value of x squared minus expectation squared of x, because I already know what expected value of x is. It's 1.5. So I can just write expected value of x squared is going to be the x squared values times their probability of occurrence. So 0 squared times 1/8 plus 1 squared times 3/8 plus 2 squared times 3/8 plus 3 squared times 1/8 minus the mean squared, and the mean is 1.5, quantity squared. Plug all this into my calculator. I get the variance of x is 3/4. And sigma of x then is the square root of 3/4, which is 0.867. And the coefficient of variation is square root of 3/4 divided by the mean, which is 1.5 or 3/2. I get 1 over root 3, which is 0.57. So reasonably strong variability, 60%. Here's another example. Let's suppose that the bearing capacity of the soil in our column footing foundation is known to vary between 6 and 15 kips per square foot. Its probability density within this range is given as this function here. If 6 is less than or equal to x is less than or equal to 15, and 0 everywhere else. The questions are, what are the expected bearing capacity and what is the variance of the bearing capacity? I usually start a problem like this by drawing the distribution. We can see that what's happening here is that as x increases, this thing decreases, and it decreases linearly. So it's going to be a triangular shape like this. It starts off highest at 6, so 1 minus 6/15 divided by 2.7 is the height there. And then as x increases towards 15, this becomes, well, in fact, when x is 15, this becomes 1 minus 1, which is 0. So it decreases down to 0. We know that this is a triangular shape. The centroid of a triangle is at the 1/3 point, 1/3 from the big end. The actual width of this triangle is 9. So the centroid is going to be 3 from the big end, which is also going to be 9. And we can check that. We can integrate mu of x is expected value of x, which is the integral from 6 to 15. So this is over all possible values of x times f of x dx. And now I just plug in the function for f of x. And then I can integrate this. I'll find that that integral will give me 9 as expected. Variance is expected value of x squared minus the mean squared, which is this 9 squared. Expected value of x squared, I just put the x squared in here, multiply by my function f of x, and it turns out that that'll be equal to 85.5. So the variance of x is 85.5 minus 9 squared, which turns out to be 4.5, and the standard deviation then is 2.1. Coefficient of variation here is 2.1 divided by, it's the standard deviation divided by the mean, or 2.1 over 9 is 0.23. Okay, and that concludes this is the first part of the second lecture in week 4. And I'm going to sign off now.